Yeah, hi everyone. Welcome to our, I think now it's like the 18th Cuda mode lecture today. I'm super happy to have a couple here today to talk a little bit about fusing kernels, which is like a way to get more speed of it and to do it in a very hands-on way. Some notes about like our format here. We normally have talk for 1 hour. Now we have changed to Zoom, which may be new for a couple of people. And if you want to ask questions, since we have no chat integrated in Zoom, please head over to Discord, where we have a new lecture QA channel. And there you can basically ask questions and discuss things. Otherwise, I think you can also ask questions in the end of the session after the presentation, or we will look what's basically in the channel and forward it to the presenter. Okay, so Kapal, if you are ready, please go ahead. Stage is yours.
All right, sounds good. This is Kapil. So I work at Meta. I primarily work on Rex's components using PyTorch primarily. So essentially, the whole modeling lifecycle, training, eval, inference, etc., is sort of my game. And I mean, as part of that, performance optimization of modeling of models is sort of ingrained in the whole ecosystem there. So I'll talk a little bit about fuse kernels, like how can you write those. But I want to be a little more sort of tactical in terms of what could be an introductory like start to like writing fuse kernels. So generally what ends up happening, so as part of modeling lifecycle, researchers and practitioners will end up rewriting their code in sort of native Cuda, especially for things like where you have element-wise operations, you can fuse them together and to get the optimal performance out of hardware. So now it so essentially, like what ends up happening, you're writing your modeling code and then you're rewriting everything in native to get performance for inference, for example. But I mean, with projects like Torch Compile and other projects, of course, like TVM, XLA is the other one. I'm not super familiar with them, but you can get sort of native performance from compiling your, for example, eagle mode PyTorch, for example. Right. So we will sort of do something similar. I'll take an example of a Rexus model that is open source called DLRM, and we'll sort of build it from scratch. So we'll spend sort of first 10, 15 sort of building some of the context around the model, and then look a little bit into PyTorch Profiler. I think there were a couple of talks recently, one from Taylor and one from Umer on, I think one was on profiling, one was on Triton. I think those will be useful. And from there, we can sort of build on the concept that we learned there here. So I think those will be useful things to look at if you're watching the YouTube recording, for example. So let's get started. So I have some of the artifact that you might need to get a little more understanding of like what DLRM is. There was a paper that was published by Meta a number of years ago. There was also a blog post about performance optimization and how to run it across multiple GPUs, etc. So that will be useful as well. And just knowing how to load up PyTorch profiler in Chrome tracing, stuff like that. So okay, let's get into the model. So DLRM, it's primarily a deep learning Rexus model. You can have different types of features. So essentially, there could be sparse features, and which are essentially your categorical features, where you can think of, let's say, a product like Amazon, for example. You have multiple different products on the Amazon surface, so you can click on it, view it, you can make a purchase, etc. So any interaction that a user has with a platform would trigger an event. So that's like, for example, what was the product ID of the product that a user clicked, for example. So and these are pretty sparse. So not every user is going to click on every single product, and not every single product is relevant to every single user. So if you think of it in pretty much a two-dimensional matrix, it's a pretty sparse, like zeros and ones. So where one is essentially an interaction, for example. If you bring that one hot encoded matrix down to just IDs, you can just save them like as interacted IDs, for example. You can go back to like word2vec, for example. That's a good reference point to understand like how you can take a one hot encoded interaction matrix down to like a single vector of IDs, for example. So those are sparse features. Dense features would be example like user age, user country, for example. Right. So as part of DLRM, you have dense and sparse features sort of interact in as part of interaction layer.
I'm sorry, like, I don't know who that is. 1 second. I'm sorry, whoever is not on mute, please mute yourself. The Discord, sorry, it's not showing them at the top. Can anyone figure out who's talking? Like,
I think it's fine now. Yeah.
okay.
Yeah. Cool.
Somebody called
So, yeah.
James V.
Jane V.
James V.
James V. Okay. Thank you. All right, seems fine now, but yeah, folks, please mute yourself. Otherwise, we'll have to forcibly mute you. And sorry, Kapil, please keep going.
Yes, yeah. Cool. So now dense. So these triangles essentially mean multi-layer perceptrons, or you can think of them as just neural networks, right? And there are a number of interactions. So dense layer goes through multi-layer perceptrons. Sparse layer also goes through a certain number of layers. Then you interact those features together, and then there's like a top neural network here, which outputs a prediction. So which would be going back to the example that I took, like you can think of like a user clicked on an Amazon product. So you are trying to predict that based on a logistic function, for example. Now there are a number of system constraints around this model. The blog post that I mentioned previously is a pretty good reference to it, but this GIF is like pretty good, which describes like what are the, like if you think about modeling and like hardware, like what are the important things that you have to worry about. So when you talk about features, like this is pretty much bounded by how much memory capacity you have, and so how much you can load in memory. Now, as part of the interactions here, you would there are embedding lookups. For example, so sparse features are converted into embeddings, which you interact as part of like this part here. So those embeddings, like the wider those embedding matrices are, the more essentially the more memory you need to hold them, and then to say the more memory bandwidth you need to actually extract those embeddings while you're doing the feature interaction there. And the last part, the top part here, is very compute intensive, because essentially you are doing, you can think of like dense layer here and the embeddings here combined together as, and if you do second order interactions of like, think of just a batch matrix multiplication of a bunch of dense features here and a bunch of sparse embeddings here, you will get a pretty wide linear layer. And if you're adding NLPs on top of that, you'll get essentially exploded weighted matrix. So which then you have like a lot of compute requirement in the top layer. This will get a little this will be a little more apparent like once we go to the code a little bit and dig a little bit into the model. But yeah, I actually, I did end up putting it. So yeah, so the interactions end up being like dense times sparse times the embedding dimension, like average embedding dimension times square. So if you're doing like cross interactions, which with in this layer. So we'll use the Criteo data to play around with it. This is like a pretty well-known data set. It's open source. You can download it, and like it has 13 dense features, 26 sparse features that go into. So we'll use that and DLRM as the model.
Kapil, can we ask
So-
question?
Sure, yeah.
Okay, so I have a question with respect to the sparse feature representation. So is sparse feature primarily represents interaction of the user with the product, or is it a combination of interaction and the product ID itself to create a kind of a combined representation? And a follow-on question is this captured at the user level, or is it a collection across multiple users so that you have a holistic view of the different interaction that happens on a particular product ID?
That's a good question. I think like that's getting too much into the modeling side of, or like I guess data collection side of things. But yeah, I think like so in this data set, these are anonymized, so we don't know what these features are. But you can think of like each individual row. I mean, you can collect data in different ways, but here we'll assume that this is just a single interaction because the label in this data set is essentially clicked or not clicked, or like interaction or no interaction. So the sparse features could essentially mean there could be different categories of products. So if this category was triggered or not, whether so I don't know if that answers your question exactly, but sorry, I lost the second question. Can you repeat that? Sorry.
I think you covered it. Thank you.
Yeah. Cool. So let's quickly just jump into the model, and I'll just like jump into code a little bit. I pre-created this like Parquet data set, so it's faster to load the data. So there's a sample data set that's on the repo. Oh, by the way, I should have mentioned that there is a repo that if anybody wants to like check out, so it should be available. I did push the code there just before we started. Now, yeah, so I just load a single batch. I'm going to load a batch size of 2 just to quickly go through. So we have a dense size of 2 by 13 and a sparse size of 2 by 26. So we have 26 sparse features. So yeah, these are, I mean, I just converted, these are like hashed. So I just converted them into integer IDs. So these are just some interaction in the sparse space. Yeah, so I mean, so just sample data. Now, if you look at the dense layer, maybe we should quickly look at the model because that actually will make things a little more clear. So this is the MLP I was talking about. This will be used for both dense and the sparse or interaction layers. So dense layer is essentially just MLP on top of the dense features. Then we have sparse feature, which is essentially a number of embeddings, so which is like each sparse feature layer, and we'll talk about it a little bit later. But essentially, like we bring the sparse features down to a smaller dimension, so we're able to like get the model running a little faster. But that we'll cover that later. And then there's an interaction layer. We take there could be different ways to interact the features, but I'm going to focus on this one, where we do a batch matrix multiplication of the dense output and the sparse output from the layers. And then there's a final prediction layer, which does the final prediction as a sigmoid. So going back here, quickly running this. So we should get, oops, okay, dense, is dense defined? Okay, dense, sparse, okay, there you go. So this outputs 2 by 16. I essentially add a single hidden layer of 32 size, and then the output size is 16. So we should get a 2 by 16 with a batch size of 2. Same thing here. We have a sparse arch. We take sparse MLP output of 16 size. So we should get 2 by 16 size. Going to the interaction layer, we take the output that we got from dense layer, sparse layer, and we do a giant matrix multiplication. So this should show you like how it can explode. So like how quickly the number of interactions is it's sort of n squared. So now you have a pretty wide linear layer. So if you add MLP on top of that, that adds a lot more weights. And now this is the final prediction layer, where we'll just do like a single prediction here. Now, I sort of produced like a model graph. This to just showcase like what ops are running as part of the model, because this will be useful when we talk about fusion. So quickly load it so it's easier to see. So if we look at, so this is essentially the dense layer where we are. There's a matrix multiplication here. This is the batch. This is the input that's coming in. So here, I think when I generated it was 32 batch size. So that's why 32 times 13. So there's a matrix multiplication followed by value, etc. And then if we go here, this is where all the concatenation is happening and the rest of it. So, but yeah, this will be useful when we talk about fusion forms. So let's quickly do a little profiling to see like what is the, so this is sort of, let's start with the baseline, how quickly our model can run as of now, and then we'll sort of slowly improve it. So what I'll do is I'll run the code from sort of the baseline that I had started with, and then jump to like what we will sort of work with as we work on the kernels part of the talk. So we already talked about the model. So in the baseline model, what I sort of did was I took all of the IDs that were as part of each sparse feature, and I just tokenized them. So essentially, like you can just map the distribution of IDs down to like 0 to n, where n is the cardinality of the sparse features. And so I'll just call it like index hash. So but it's sort of just a tokenization, pretty much. And in the sort of, just to showcase like how important memory, actually having data directly on GPU is helpful. Like we'll just do a really bad version of like what the code might look like. So here I have a mapping of the tokenizer values, which is essentially IDs to indices. And then we have a hashing function here, forward index hash, and we will call this function as part of the forward. So let's go on model trains. Should take a couple of seconds. It just runs a single epoch. And I'll just load up the trace. All right. So when I started out, like I had forgotten a couple of things. So now you can see like, so I also doing it with trace. So now you can see like where like each part of the code in the profiler trace. So so here, like I mean, if you look at DLRM, most of the time is being spent in the hashing. But we previously talked about how this should not be the most compute intensive thing, right? So versus we should actually have the prediction layer that should be the most compute intensive thing. So anyway, so the reason why is like we have a bunch of these, if you like just look at the ops, like there's a bunch of copies happening, and and you're just spending so much time just copying data around. This is not super optimal. So I mean, so going back to here, like we are essentially think as tokenizers on every single forward, we're copying data over and moving it to device. So now let's make it a little, let's make a little improvement, and we will comment this out and and we'll uncomment this. And now, so what I did was I just moved everything onto the device, and now things should look much better. actually going back here, let's also get a baseline of how much time it's spending in the whole thing. So right now it's saying around 53 milliseconds. So another thing that jumped out to me when I started working on this thing was like this ATAN call. It's like why is it taking so much time? So I think like probably like a bunch of folks already know the answer to this, but like does anybody have a guess like why this is taking so much time here? Maybe just shout it out if anybody knows.
So I would like I guess that it maybe like is waiting for the GPU to complete it because it causes sync, maybe.
Yeah, exactly. So it will, so the profiler will wait on the synchronization step, right? So like so this item is coming from when I'm grabbing the loss value, and it's just waiting there. So the timings are not quite right. So get things actually like showing or get profiler to show things correctly, you actually have to I believe like a couple of folks have already covered this flag. So if you pass this flag, I think things look a lot more like sane. So let's call this again with quickly just adjusting the profiler, because that's going to give us different timing. So like if you look at this one, we actually saw around how much was it? 53 milliseconds. Now let's see how much that shows us now. I'll load up the one. So let's go here. So you'll start, well, actually it didn't change that much. When I was doing some experiments, it changed a little bit, but you will see that the item, the ATAN item thing goes away. So so things look a lot more same. Now you're basically seeing the backdrop step and stuff as part of the optimizer step. But yeah, from here, so now that we have a baseline understanding of like what the model looks like, I'm gonna just fast forward to like the most optimal hash I could think of, like just to iterate on this faster. Like I essentially just took the cardinality of each sparse feature and just modulo hash it. So which will be I mean, it's a simple operation. So something like this, and so completely bypass the index hash to see like how can I squeeze the sparse hash to like be a little more optimal, right? So now just gonna move to this one. To be honest, I actually had a lot more profiler stuff here, so which I had to cut out because I think Taylor's talk was so good that then I had to like I sort of, but that's good actually. Then we can focus on kernels more, so that's kind of nice. So okay, so like now jumping to the forward modulus hash. Now let's run the profiler again. Now this time we're gonna run with Cuda launch blocking. And let's load it up once it finishes. I have two screens, by the way, if you're wondering where the trace is coming from. So I'm just dragging it from the other screen. So yeah, I mean, it got better, right? So I mean, prediction layer is at least visible now in the trace, and you can see like how bad originally things were. Like it was 53 milliseconds, we dropped it down to 4 milliseconds. So you should just see, like if you increase batch size, for example, this will be a lot more, I mean, lot better. Right now we were just running with a small batch size of, I believe it was 16 in the small config. Our batch size was 64, but I think I was running, oh yeah, I had fewer hidden layers. So I think that's why so complexity of the model is pretty small. But yeah, let's increase the complexity to see like how much of a now like what portion of the performance is now coming from sparse hash. So because that's gonna give us a bit of a realistic picture of like how performant it is as of now. So I do have a bunch of stuff here. I think like but that's I think this is sort of folks can read it afterwards. But jumping to so we got to here. So modular hash. And now let's increase the complexity of the model. So let's go back to here. So what I'll do is in the bigger config, I'll add a lot more hidden layers. So that will increase the number of computations that the backprop step would need to do, and also I'll add more hidden layers to the dense MLP. I took these values from the actual blog post where they actually like they specify like these are the dimensions that we took as part of the as part of that study. So let's run this again and with the bigger config. So that will essentially now give us like we're running now the actual config that the actual DLRM paper ran. I think embedding sizes are smaller. That's because I can't fit things into my GPU if I increase embedding sizes. So there's that. So yeah, we got a new trace. Let's open a Chrome. All right. Things should look different. So let's see now. So now you see, like I think the things are starting to make a little more sense based on like what the original paper had said. That okay, so the prediction layer is definitely it's taking a lot more time now. And if you look at the actual summary, it's taking 16 milliseconds. So we were at 4 milliseconds with this with the smaller hidden layers or like fewer hidden layers, and now it's jumped up to 16 milliseconds. So from here, I think so. So this is like so I want to sort of build some context around like what the model is and where the complexity lies, right? So now what's the next step? As let's jump into the feet of a researcher. Like you have a model that's training, and it's like let's say you have working model. It's running pretty slow. Like what's the next step that you can do? You'll either go to an engineer, like partner engineers, like okay, like can you help me optimize this, or you can just run torch compile, which is what I did. Because I mean that's so. Now, let's see how much of a boost we can get if we just use torch compile. And so we should expect torch compile to do something, right? We have a bunch of, so just to build a little bit of intuition, as if we go to the MLPs, like you have a bunch of sort of element-wise ops that you will be doing. Think of things like once you have weights. So once you have matrix multiplication done, you're doing like an element-wise like max on the output. Plus, you're probably adding a bias value. So I mean, you can think about it. Those are all parallelizable. So and you can probably put them in a single kernel if you were to do something like that. So now the interesting thing is like, can torch compile do it for us? It's something I wanted to test out. And so yeah, now that this is done, I'm gonna load a new trace. So
by the way, could you show in the code exactly what torch compile does, or what you basically where you apply it to which function is?
Oh sure, yeah,
that would be like very interesting. And also, do you use like specific parameters? Is it, or do you have like always static tensors, so there's no dynamic like size changes happening, or forward passes are the same size?
Yeah, so yeah, I can quickly cover that. That's a good question. So I mean, I do it with full graph, so it will essentially raise an exception on a graph break, and I do it in the max auto tune mode. I actually don't know what that does. It seemed curious, so I tried this one. I think there's a bunch of different modes that you can try. But yeah, I am assuming that. So I'll show that later when we look into the actual torch compile artifacts. So like most of the code is actually running on static size, and actually Torch Compile can figure that out from the inputs. I think things get a little more complicated if you have dynamic sizes in your models, but this is like fairly trivial. We don't have anything sort of like expansion or like reduction in the tensor sizes in the modeling code, so which makes it a little more simpler.
Thank you. And one like follow-up question to this, maybe also to Mark, is like in this case is like where you have the static shapes. How is like how does it compare? Like how does Torch Compile compare to like Cuda graphs, for example? Is it like would it also be possible to use Cuda graphs as in this case, or I don't know if you have tried this, but or is it like conceptually it can't be used in this case, for example?
Yeah, I can answer that actually. So Torch Compile, you can think of it as like a applier of two things, like one of which is fusions, and the other is Cuda graphs. So if you're using mode max autotune or mode reduce overhead, you're effectively using Cuda graphs.
Right.
And the only reason why Cuda graphs isn't on by default is because it has a slight memory overhead that would make a certain class of models that didn't all of a sudden if they're at the very limit, which is why we can't really turn it on by default. You know, I've been pushing that maybe we should, because it's just such a dramatic perf improvement that most people would probably want, but we do have to debate these things. The other interesting thing is like Cuda graphs typically also require static shapes. So the workaround to make it work for dynamic shapes is you basically compile with Cuda graphs for like a bunch of shapes, and then you cache them all. And so like you can actually use Cuda graphs with dynamic shapes and with Torch Compile. And this example is using Cuda graphs too, is really also my point.
Yeah, so yeah, that explains some of the traces that I'm going to show later. But that's actually good to know. So actually one question to Mark that came to my mind. So like you can technically also like use padding in some way to like essentially just specify like this is the static size I'm going to maintain, and then you basically just pad a bunch of values. So you're always keeping static sizes, but you have some way to identify like either you can have some offsets defined in your modeling code to like just reference back to like, so if something is changing dynamically, you can sort of have a padded value like pre-allocated or something, which could allow you.
Yeah, so regarding padding, you're correct in that like if you can make your code static, generally for perf reasons, that'll be like the best thing. If not, the main thing that tends to change in LLM code is like the sequence length, for example. So like as long as you have a fixed range, that's usually fine. But like I think where things get really interesting, and there's like a long thread about this, if you go to the PyTorch GitHub, is getting Torch Compile to work with nested and jagged tensors. And I think that's really what people actually want, because people don't like like padding introduces like both a memory overhead and a time overhead, but not padding, you know, yes, you can do dynamic shapes, but it's not going to be as fast. And so, so I think what we're going to be moving towards is like I said, like working better with nested tensors. So you could have tensors that naturally, like nested or jagged means it's not rectangular or square. It can have like a jagged shape, basically.
Yeah, makes sense. Cool. And so now I know what so max autotune does as well. So that's cool. So okay, so let's load up the trace. Which is actually loaded already. I think I loaded the. Let me just make sure I have the right one.
Mark, I had a quick question.
Sure, yeah.
So doesn't Cuda graph have a dynamic mode as well, where it traces in the first few rounds? Uh, does that not work? I mean, so I mean, if it probably picks up the shapes of the kernels based on the first couple of runs, and so I think it has a dynamic option as well. So
Yeah,
there are two ways you can build the Cuda graphs, right? One is a static one, where you just assign which kernels are in the graph, and the other to like let it trace and pick up the kernels as it goes.
Sure. So, like for what it's worth, like I'm not an expert on Cuda graphs, but like my understanding of how their dynamic shape support works is what I described earlier, which is like you basically just try multiple static options, and this becomes like your source of dynamism. I think for more like I can see if we can potentially get someone like Elias Ellison from the PyTorch core team to come give us a talk because he built out the Cuda graph support with Torch Compile, and he might be much more familiar with these nuances than I am.
Okay, thanks.
Cool. So that's the data order. So let's go here. Okay. So now, I mean, things should look dramatically different. So, so we still have the DLRM that you can see top layer, but now there's this like, torch compile thing, which essentially has a bunch of AOT inductor code, and but yeah, what like a couple of folks asked about, can actually see that there is a Cuda graph launch call here, which is essentially launching a bunch of kernels, which is interesting. And I mean, there's also like a couple of launch calls here. Seems like Atan Phil is probably doing some op to like copy things over. So you can actually jump into the stream to figure out like what kernels are being launched here, right? But yeah, the Cuda graph launch is actually the most interesting of it. So let's jump here. Now, I mean, some of these will look familiar, but yeah, so there's a gen call here. So there's some matrix multiplications happening, but now you start seeing these Triton kernels, right? So this was definitely super fascinating to me. Like, I mean, a couple of months ago. Now it's like second nature. But yeah, but cool. So I mean, it's seen this calling a bunch of Triton kernels on the stream here. Here's another one, and you can actually jump into it, and it actually has a sort of a name, which you can map back to. Like, so, but I'll show how to sort of do that. One thing that's also useful, like I don't think that was covered in some of the tooling stuff that we've covered so far, is like TensorBoard. You can actually push like all the profiler trace some data to TensorBoard, so you can actually view a pretty good summary of things. So I'm just so I've been putting all of the logs here, which has all the traces. So let's just load up TensorBoard quickly to see like what sort of stuff we can look at. I'm actually putting everything on it, actually most of the things. So I'm putting memory, and with stack, it just gives us like the nice looking like where in the code things are happening and stuff, and recording shapes, etc. So going back here, now we've covered some of this, I think, like through some other tools, but like it actually shows you like actual GPU utilization, which is sort of nice, and like shade memory efficiency, all of that stuff is pretty nice. And like for this specific example, like I want to see the kernel calls. So I have two separate spans, like one was with torch compile, one was without. So we can check. So it seems like this fill functor kernel, or like element-wise kernel, is actually the most called kernel. But if you look at span 2, which was the torch compiled version, now you start seeing these Triton kernels on here. So what are these Triton kernels? Like what's happening in them? I think that's now the next sort of curious question to look into. So PyTorch comes with like a handy way to actually output that. So you can do some, there is an argument, so you can set an environment variable on torch logs to output code, and it will put all of the Triton code that it generated, which is running in a folder. I think it puts it in temp. And from there, you can actually see like what kernels it generated that are running as part of that Cuda graph. So I'm just going to try that here, and let's quickly load up. takes a couple of seconds. So yeah, so it shows you like, oh, it just put all of the code here. So I'm just going to open it up here to, let's see. All right. So I mean, there's a lot of, so when you first look at it, it looks very gibberish, so like it's hard to follow what's going on. But the interesting thing is this is actually a runnable Python file, so you can actually run it, which is cool. Now from here you can actually trace back like what's like, I mean, it's calling this function. Let's go to this thing. It's let's go back here. But okay, like, so stepping back, so it essentially calls this giant function over here. And now some things will look pretty familiar here, like there's a mat mult happening over here. And now you see these like Triton POI, fused ReLU, etc., etc. So I mean, yeah, things are starting to make sense. It's running a mat mult, then it's running some fused kernel over here. So let's just quickly look at like what's going on here. Now 13 should look familiar. Like we had a 13 size dense tensor. So it's taking this so arg01, which is essentially this 13 by 512 by 13 tensor. This is most likely the weight matrix because 512 was our first hidden layer. And it's multiplying it with this arg 41.1. So our batch size was 128. So this is the input. So 128 by 13. So you're basically doing a mat mult here. And if you're wondering like what this reinterpret tensor is, I believe this just generates like a strided tensor to pass. So I dig into the C++ code for this. Like it's a C++ call which actually sort of specify the strides for each tensor. So strided tensor essentially like you can think of a tensor defined in just coalesced memory, and then you can reference back to like if you had to transpose, you can just change strides to be able to reinterpret the same memory as a transposed tensor. So, but I'm not an expert on like what exactly is this, like, but yeah, it's basically you can if you had stride of like if you had a 2 by 3 matrix, you could have strides of 2s, which then you'll jump over for every row. If you had a 3 by 2 matrix, so if you transpose that, you will just change the strides, and then you're able to get the transposed tensor.
So, Kapil, do you mind if I jump in there? Because I think this is a really,
sure.
really
Yeah. Yeah, cool.
So first off, like when you see the Triton POI there, like what the POI stands for is a pointwise operation. And what a pointwise operation is like an operation that applies over every element of like a certain tensor. And so if you have many pointwise operations that are all done one by one, those are very naturally fusible. And so what you're now seeing is an example of a fused kernel. Example, let's say the pointwise op was you add 1 to every element. And let's say you're adding 1 3 times, you can just add 3 once. And so this is like a very natural way of thinking about like the benefit of fusions. Like instead of dispatching multiple kernels that adds 1, you just dispatch a single kernel that adds 3 once. The other thing is that like with this reinterpret tensors, actually this is kind of like, it's not like a secret per se, but like if you go through the PyTorch like onboarding docs, like one of the first things we try to explain to people is like how powerful striding is. So with striding, for example, you can implement like broadcasting. You can implement like transpose. You can flip something. You can take the diagonal of a matrix. And so it's kind of like one of those, if you like to think of things in terms of like algebra, it's kind of like one of those very core operations that you could then use to implement a whole bunch of other operations. So for example, like let's say you want to change the layout of a tensor to be channels last instead of channels first, you can use striding. Let's say you want to pad something, again, you can stride. You want to pad and reshape, again, you stride. So like striding just is one of those very, very powerful operations. And you can get a good sense of the power of it if you go through the PyTorch onboarding, and I'll just post the link in the lecture Q&A. So yeah, just
And
to
after
digress.
all this, and after all this striding, then the developer puts in a contiguous core to make it all.
Yes.
Thanks, Mark. That was useful. Yeah, so as Mark said, so yeah, I mean, so now, so like essentially, like the first step is like we have this matmul that's happening, followed by this pointwise kernel, a pointwise fuse kernel that's being launched. So, like what's being passed here. So like just to reference back to the model, like what's happening here. So buffer 1 is just buffer 0, going back here, buffer 0 just the output from this matrix multiplication. So you can think of it as the input times the first weight matrix that you had, which was 513 by 512. So you should get a 128 by 512 matrix as after that. So which is what this 65536 is. There's a lot of hard-coded values here, which sometimes becomes hard to follow. But if you actually go back to the actual inputs, it makes a little more sense. I actually wonder like how this would be with dynamic shapes, which I haven't played around with much. But yeah, so let's jump. Let's jump to this kernel. So like we have this arg11, which is it's a 1D tensor, so which of 512, most likely the bias, because bias is the 1D tensor. So so yeah, let's go up here. So yeah, this is the actual Triton kernel that it's launching. So again, it has a bunch of hard-coded values, and it's mostly because all of the sizes are static. So now things are starting to make sense here, like because we've sort of covered Triton before. But yeah, like all of this is pretty standard Triton stuff. You have this separate. You basically this is your block size, and then you basically have these indices, the thread indices, and then from here, like you're figuring out like okay, like this. So it just copies over into x2, which is again the same index. This part is interesting, which is it's doing modulo 512. So where is x0 used? So you can just see like it's used in the input pointer 0, which was the bias. So that makes sense, right? So essentially what it's doing is doing something clever. Like it has the whole set of indices, but it's just doing modulo 512. So you always remain in that like single row dimension. So it seems like the it's running row, sort of like row by row blocks of the tensor, right? So yeah, I actually like what I did in the notebook. I put the actual kernel down. So let's see here, and I just annotated it as like essentially like an explanation of what's happening. So you can literally like you can copy paste these Triton kernels and like put it in a single Python file and start experimenting with it. So this is what I did to start poking around with like, or like how can you extend it? How can you like have it support like other different ops, for example? So yeah. But yeah, like jumping back to the file. So yeah, that was the first sort of fuse kernel that it is doing. Like it's doing an element-wise operation. There's a bunch of other ones. So if you start scrolling down, like you'll see a huge number of kernels. It's also doing like some point-wise fuse embedding, and then there's another one at the end. But yeah, like the point is like you can actually output this code and start poking around with it to see like how Torch compile is doing things or like improving things for you to be able to run faster, right? And like once you start seeing like these generated kernels, they can reference back to here to check. So yeah, outputting code is like super useful to just sort of have like it is sort of like a learning guide to like so if you wanna if you are like I mean I learn things like top down, so like go to a complex thing and just like start poking around from like from the top layer and just start peeling layers. Like from that perspective, it could be pretty useful. So like you have an existing model, you run Torch compile on it, and you see like it did generate a bunch of kernels. So how like it could give you like pointers around like how you could potentially improve your code to like give you better compiled code. So now since it's Cuda mode, like I mean, I guess like before we get to Cuda, we can just, I mean, I copy pasted this kernel into just a simple Python function. I pass like a single once just to see what it's doing the right thing, and like it should take, this is ones of 512 by 1, 128 by 512, so it should give you essentially this result. And yeah, I mean it matches. So I mean we can poke around with it, and let's say we did something like -10. Now this should not match. So it should all be zeros. So yeah. Cool.
Yeah. So if you like, there's also like an environment variable like Triton underscore interpret. You can use it to just add print statement directly in the Triton kernel. But yeah, I like what you did with writing the torch code as well, just sanity check. That's also interesting.
Yeah, I actually learned about it yesterday. It's like, yeah, now you can start printing out, which is actually super nice. Yeah. So Cuda mode. So yeah, I think like if you I mean if you have a generated if you have a Triton kernel, you essentially have Cuda code pretty much. But ChatGPT is actually pretty good at generating Cuda code from Triton code that's sort of well commented. So this is what I did like that. So that was the exercise I did here. I basically commented this code and just put it into ChatGPT to see if I can taking inspiration from Jeremy, who did a bunch of like ChatGPT based code generation. So and I took this and it actually ran correctly the first time, which was awesome. So yeah, I mean I put a bunch of this like generated Cuda kernels into there is a directories with kernels. There's a CMake project there, so you can just compile it and run these. So I sort of already did that. But yeah, I mean you can. I mean all of this is just like runnable code. Maybe we can quickly run this. This ran fine. So probably wouldn't take time to compile because I already compiled it. So yeah, no, that's cool. So yeah, I basically did something similar in the code here, where I ran everything in the so let's go to this one. So this is the generated kernel. I sort of cleaned it up a little bit because it had a bunch of like intermediate variables. So I just simplified it a little bit, and then I essentially defined the same block sizes, threads per block, and I'm able to call this on like this regular torch tensors, and sort of did the same thing, like call this add a leaf fusion kernel you on just two random and see it makes sense. So yeah, I mean, but yeah, the interesting thing was the Triton to Cuda conversion was pretty interesting. I mean I don't know, it's the practically I don't know how useful it is, but I mean but yeah, I thought it was sort of an interesting exercise to do. And I think this was sort of.
I would suspect the Cuda code here is much slower, right? Like, did you get a chance to run it?
Good question. I didn't try to run it. That's actually I should have. Yeah, but I didn't try to run the profiler on it. That could have been interesting to look at. Yeah.
Yeah, like my suspicion is it would be the default Cuda code would be quite slow, because like I think with Triton, like they sort of rely on their like compiler stack to sort of eventually also further down the line code generate like efficient code. But I think with Cuda, it's like there's not much I think there in terms of like there's like a lot of the tricks we talked about with Cuda that probably need more work here. Which I guess like I think writing naive Triton code on average tends to be more performant than naive Cuda code. I think that's like one of the benefits of having something like a slightly higher level.
Yeah, that makes sense. Yeah, I mean that's basically like if I mean I think that's like if you go another layer up like from like for Torch compile, like that's so you're essentially writing eager PyTorch, and like Torch compile is giving you like pretty performant code just out of the box, which is pretty awesome. So yeah, I mean this is I think probably not worth covering it, but yeah, this we sort of did a similar exercise previously. You can actually just use the load inline to generate a Cuda extension to just run the code inline. I think this would have been a good place to actually run the profiler on the Cuda extended ReLU Fusion and the one that we generated from Triton. But yeah, I mean, so I think I guess like we are at I guess how much time do we have? Can we go on for 15 more minutes? So this was just a case study.
It's up to you, because I think we've been asking you questions along the way, but typically we go for like about a max of like an hour and 30 minutes. So you have like another 30 minutes to do with that time as you will, if you want to, you know, because we do want to keep going as well.
Cool. Yeah, I think like the next thing is, I think mostly building upon what we already did. So, I mean, I just want to highlight like, I mean, which I've been trying to say all along is like Torch Compile is your Triton learning companion. So it's essentially like if you want to dissect bigger systems, like through Torch Compile, like it can be super useful to learn Triton along the way. So I mean that's another approach. It's like so anyway, so I think like so the next section I sort of cover similar content as we did from like, so we started with the DLRM eager model. We sort of optimized it a little bit, used Torch Compile to start poking around with like what were the fused kernels that we generated as part of the process. So let's try a different model. Like, I mean, LoRA is like is really hard like for fine-tuning LLMs. So I thought that could be an interesting exercise to look at. And LoRA is not really specific to LLMs. Like it can be used for any model for fine-tuning. So sort of an interesting example. So to sort of, I mean, quickly cover like if for folks who are not aware of LoRA, as part of fine-tuning process, let's say you have a huge model, you want to sort of fine-tune it based on some new data. You can do it in sort of, instead of updating all the weights directly, you can sort of do it in a low rank space. So you take the weights and like sort of project them into two matrices A and B, which are sort of low rank, and so you're able to sort of get the same dimension. So the sort of the analogy is like if folks are familiar with like eigenvalues, eigenvectors, you have a certain amount of information in like n subspaces. You and you can think of it the SVD rank or the rank that's used in LoRA to be like let's say you take the top 3 eigenvalues and you sort of encapsulate all of the information that was available in the n subspaces down to those like top 3 or top 4, for example. So so as part of fine tuning, I think the point that the paper sort of made was like a lot of the information was only in like first n subspaces. So you can actually like fine tune using fewer dimensions. But yeah, I think the paper is a lot better reference to like look into like how LoRA is useful for LLMs. And it's actually using SVD in the background to do that. So I essentially wrote like a sample small model, which was so it's a simple MLP. Like I take a linear layer followed by an activation, linear followed by another activation. Like I mean, just the stupid little model, which like and you can sort of inject the LoRa layers into this model. Let's say this was a large model, right? And you can inject the LoRa layers within this to generate sort of a fine-tuning model where you sort of freeze the linear layers and then you only update the LoRa layers as part of your fine-tuning process. So I mean, this will sort of just also like drive home the point around like if you had more ops done as part of like point-wise operations, they can all be fused. So that's why this is sort of just a slight extension of what we had already covered. So so yeah, let's inspect the code again as we did with the DLRM code, and I'm gonna see storage works. Okay, load on simple MLP. So we'll just quickly run that. So here also I do I just Torch compile, max auto tune, and I pass like a batch size of 7 So just easier to track like what's going on in the kernels, even though the generated code should be much smaller. So let's go here. Not sure what's this. Alright. So here you see, like, I mean, previously we looked at like Triton POI fused add value. Now it's adding a multiplication on top, but the point is the same, right? It's basically doing something similar, but it's just like doing a bunch of extra operations on top of. I think it's just a multiply with a scalar, but you could think like if there was a multiplier with a 1D tensor, for example, like for like a Hadamard product or something, that it can do. That should be technically be doable in a fused kernel as well. And so there's another one here. So it's the second sigmoid, the second activation, which is sigmoid, has also been fused as like an admil sigmoid. So, and going down to the actual place where the code is called, you can see now that so previously we had like a single matrix mult followed by a fused kernel. We have 3 matrix multiplications, which sort of makes sense. We are doing now going back to the LoRA code. Okay, there you go. Going back to the LoRA code, so you basically should see a matrix mult here, another matrix mult here, and I believe I didn't, yeah, and then the actual linear layer. So your 3 matrix multiplication followed by an activation, essentially. So which is what it shows here. Now, I mean, I essentially just did a similar exercise on this, and like again, all of this should look pretty similar to what we covered as part of DLRM. But I sort of generated this kernel, ran sample data. Another interesting part is like it's actually taking 2 separate tensors now, I think. So it's fusing 2 separate tensor operations instead of 1. I mean, but at the end of the day, it's conceptually it's the same thing. And you can do the same thing. Like you can essentially, I was able to just copy paste it into ChatGPT to generate a Cuda kernel, and that ran perfectly fine as well. What I did was like I wanted to sort of have a tutorial style, because this is actually where I started the talk. Like I was going to do a more like math oriented talk around like LoRA and stuff, but the talk actually took a very different direction. So because I got super curious about touch compile. So but yeah, so just to so essentially like we can take this fused kernel that was already generated, and we can sort of maybe let's have activation as an argument as well. So you can have sort of all activation done as part of a single kernel, right? And what I did was I generated a Triton benchmark. And so let's go here. So yeah, Triton has, so like essentially to see the actual the arithmetic intensity graph for the fused kernel to see like whether we're hitting the peak or not. So actually, let's go here. So I mean, I think Umair also covered some of this earlier. I think 2 or 3 talks ago. Essentially, I'm calling the actual kernel that we took out from Torch compile code. I'm running, this is essentially just eager PyTorch, and I wanted to check it against Torch script as well, because it's sort of like still Torch script is around, so like people use it. And I think like some of the Triton benchmarks that the OpenAI did had Torch script there, so I thought it would be interesting to look at. So let's quickly run this. So it should be Triton fuse AdMul activation. And it should show us the arithmetic intensity graph for everything. What was interesting to me was like TorchScript and Triton was pretty close to each other. So I mean, I was trying to poke around with the actual trace to figure out like what might be happening here, but like they look pretty close. Actually, like if you think, go back to home. If you look at it, I think TorchScript is also almost edging Triton, which was sort of interesting. I'm not sure whether it's just because it's static sizes or like, but yeah, that's, and this is eager PyTorch. So you see this, it sort of plateaus like pretty quickly, like at a much lower, right. And I was actually playing around with the actual the flags to like run the tensor cores, but it seemed like it was already, because these flags didn't really have any effect on the kernel performance. So yeah, so I think, but I'm not an expert. Like I think that probably somebody like Mark might have more insightful thoughts on this.
Yeah, so the main flag is going to be, it's called like set default float precision, and then like it takes as an argument high. But yeah, like I think the other way is just to do it based on like memory bandwidth. Like I don't know here what kind of GPU you're doing, but just like some, so you can get like some rough estimate of the kind of bandwidth you're seeing.
I see, that makes sense. Yeah. I mean, I have a, yeah, good.
The other thing I wanted to mention, like the kind of cool thing about this approach as well, is like we had like someone on the PyTorch team, Driscosus, who also code generated LoRA kernels that were competitive with bits and bytes, just writing pure PyTorch and like code generating them. So this is kind of cool. I agree with you in that like this is like educational, and if it's like educational to write Torch first and also get performance, then you know why not? It's so yeah, like the LoRA work is like already out now in like a repo called AO, and then we're cutting a release with this feature next week, you know, so that it composes with FSTP and all this like nice stuff. So yeah.
Nice. So was it just using like Torch, like bitwise operations, and then just LoRa on top of it, and was able to just generate like, yeah, might be interesting if you can put that in the.
Yeah, that could be maybe its own talk, but like essentially we just write like an NF4 tensor and then just code generate efficient kernels for it. So it's like, yeah. Well, I can say, you know, maybe I can give the talk. I'll figure out if Driss is also interested. Maybe we can get him on board.
Sounds good.
So I have one question regarding Torch compile and like to which extent it can be used. So we saw, for example, in one of your kernels there, it was like in this one, which show here, you have this activation, which is like comparing with the string and so on. So for me, always the question is like how much, like for example, control flow statements and so on, can there be in until there are graph breaks? What's the general mode where Torch compile really works, like out of the box, I don't have to do anything with, and whereas like it's challenging. And does it also make sense then to break down this manually, or is like Torch compile with this graph breaks taking care of it like automatically? Yeah.
Yeah, so my understanding of Torch compile is I think like you can so it will default to like the Python runtime when it's not able to optimize it further. I think there's a bunch of flags for you to be able to sort of handle dynamic shapes, or like if there's control flow, I think that it will most likely go to the Python runtime to figure out like which branch of the code it needs to run. Again, like I'm sort of still new to like how Torch compile like fits into some of these like sort of weird edge cases, like which you do have in like real infrastructure code, right? So, but yeah, ideally it should be able to generate code for you. Like and there is a way to like I think like some of the PyTorch tutorials go into it. You can actually just go step by step. So, for example, with inductor, if your code is failing, you can actually go one layer above. So you can just run with AOT eager, and you can see like where it's failing, and from there it gives you some indication. And I think like I actually put some flags in.
Yeah, can you, for example, like the common case that I had in the past week actually was like complex data type used, like torch distributed used, what else? Like something like this where I got like directly from torch 2.3 like errors, it gave up, and said no, torch compile not going to work here.
So yeah, I can comment a bit about this. Like I think Andreas, like point taken. Like I think we might need like a torch compile user perspective session. Like basically, I've had to myself work on a lot of like bad public benchmarks and like make sure people are using compile correctly. So that might be helpful. And then I think also like in internals, especially with like inductor, might be I think very useful for this group. There were, by the way, like I think we do need to pause for Q&A.
Yes.
Before I go into more questions, like please everyone, like we should like thank Kapil a lot, like for his time. So make sure to react here, and if the emojis aren't great in Zoom, you know, post them on Discord. And I'll start like reading questions in a second because I saw that there's a bunch of really good questions in chat actually. So I'll be going over this.
That sounds good. Yeah. Yeah, I think the last thing I just quickly wanted to cover was like, so I was wondering whether I could fuse the whole thing. Like, so can I write, like, can I take the matrix multiplication part into a fuse kernel as well? Just out of curiosity. Quickly realized that was a bad idea. But just so what I was trying to do was like, can I do like the block multiplication with the activation in the same path? But I mean, it's wrong. But I would like maybe somebody has an answer like why that's wrong, like why that's not possible.
Yeah, so there's actually, I think, I see Umar asking this question in chat. I think it's a very good question, so I'm just going to read it and then we'll answer it. So is there any downside to fusing? So if I have a long and complex operation, should I just try to put everything into a single kernel? Why or why not? And, you know, how do I decide how much to fuse? Okay, so the conventional wisdom on this question is like there's two aspects to it. Like one, writing like a mega kernel is more challenging because it has more things. And if you have like one mega kernel, but then there's something that changes like the activation, then you need to write like a new mega kernel. So there's like a code composability and maintainability question. However, I think that's not what Umar is asking. I think Umar is asking about performance. In the case of performance, the trade-off basically is if you have one mega kernel, is you basically end up having with very high like register spillover and contention on your registers, and this will generally tank your performance. However, I think this is like this at this point might be old wisdom. NVIDIA did introduce a really interesting concept recently, maybe not so recently. Vikram might correct me, but it's like the idea is called persistent kernels, where you basically have a single kernel that like runs all the time on your device, and then you stream in batches to it. So the kernel essentially is basically a proxy for like an entire network. I haven't seen too many people do this kind of work. I think it's really interesting. So it's kind of one of those things where I think it would be very helpful to do a working group, like run benchmarks, and basically like measure whether fusing everything into persistent kernel helps or not.
So persistent kernels came in a bit long ago, since the Pascal generation timeframe ish. So it's been there for some time, but not many people are using it. One of the authors of PPMP book, PMPP book, Izzat, he did his entire thesis on persistent kernels. Yeah, so he's going to come to and give a talk. I think I'm spilling the beans already. So he's going to come and give a talk, and feel free to ask this question on where does persistent kernel stand and where it's actually headed towards. How would you actually build a mega kernel with persistent threads? I think he will go in lengths.
That sounds wonderful, actually. Like, I think we could always sign him up for 2 talks because, like, I think it's been sort of a recurring question where people just don't understand why do we not have mega kernels? And I think the only answer is this like one long thread on Stack Overflow, and that's about it. I think I haven't seen too many public benchmarks.
So I always love to do long mega kernels if given a chance. But every single time when we go in that direction, the kind of question that we get into is like, stop breaking my brain. So
It's
there
too
is a
hard.
point where, yeah, there is a point until where you can actually make and understand what happens. Beyond that, it is a bit hard for humans to really follow through. Like, okay, how do I understand all the variations of the capability? Like where to optimize, where not to optimize? How do you build a global synchronization kind of capabilities? It just becomes very hard. It's the code composability, as you rightly put it, is one of the challenges that it has. But if you really want to go in that direction, there is nothing stopping you. Go for it. I think you'll be able to get better performance if you are very clever about it. For instance, if you can do data movement between the kernels in the L2 cache itself, and careful about how warp scheduling basically happens, you probably will never go for your DRAM. So you will probably be able to pipe the data from warp 1 executing certain operation to warp n executing some other operation over L2 through a pipe. And that would be like amazing speed up that you'll be able to get completely on chip. So
I think like one thing that hasn't been mentioned so far also is like one of the motivations probably for fusion, beside of like making like arithmetically more intense, and it's probably like also memory, yeah, that we don't need to store basically the intermediate results, but we just compute in one go. Otherwise, we would basically do it in like create like an output similar size of the input for point-wise applications, and then do this for multiple times. And yeah, this gives us, of course, in this fused case, an advantage there, I guess.
Yeah, I intend to cover it. I think I forgot because there was some stuff. So, but yeah, this was the example. So the original DLRM example, for example, where we were doing, this is the eager mode, and this is the torch compile mode. So you can see like the allocation is like a lot more so you can see like it's allocating and then deallocating. And it's like pretty consistent. So the memory profile is much better, and also like the amount of memory used is like much less too. I mean, it's most likely because you basically like in place updating the matrix that had the input times the weight matrix, right? So essentially you can just doing everything in there. So you don't have to do extra allocations as part of the next operations, for example. That was my understanding of like how flow was going.
And Vikram, I have run like one question, because like this mega kernel thing, I have also like to think longer about this. But for example, let's say I have like multiple reduction things in my kernel. So for me currently, I think always of these reductions, for example, that like most of the threads basically are end, and I only like on fewer of the threads basically compute my results. But if I would now like have this multiple stages of things, what would I do with like the original threads, or how would I like, what's the good way to like schedule these like multiple operations in to happen one after another? Is it that I like may have, I don't know, like do that way use synchronization options in some sense, or yeah?
So, you're actually giving me a hard question, and it's not that easy for me to answer. So if you, I mean, fundamentally, what you're looking for, is there a way for us to create some sort of like a global synchronization within every thread or every warp that executes before the next warp basically happens, right? So there is a clear-cut boundary to know, hey, this particular reduction operation across all the operations that I'm supposed to do across all the data is actually complete. So can I proceed my next set of operation, pipeline it together and make a forward progress? The technique for this, you can't do a global synchronization across all the threads in the GPU. If you want to go in this direction, you have to build some sort of like a communication primitive between two kernel computation, launch the two kernels, and do a communication between these two kernels, have some sort of like a producer-consumer relationship, and ensure you actually have the other kernels warp starting to execute if certain set of data is already available. So you have to think more of a event-driven execution model, and running an event-driven execution model in the GPU by launching different set of operations. Instead of launching 2 specific kernels, you can do maybe you expand your amount of work that you're doing within a single kernel, dedicate 50% of the work done for reduction, another 50% of the work done for the other set of operation you're doing, and have certain flags or something to tell, okay, for this particular data that your computation, I have finished the reduction operation. So the next operation, maybe you're doing a scan, I can proceed and do the scan operation. So I have a flag which basically says, go do the scan. But if the warp that gets scheduled, then it has to check whether my flag is currently available. And if it is available, then it has to proceed. Otherwise, it goes back to sleep. Let it go back, right? So you have to cleverly play around with the scheduler and make operations to execute and make a forward progress by making your work go to sleep, not go to sleep, activate, not activate, so that you move around with all the warps in a correct fashion. Does that make sense?
Yeah, thank you very much. I think I have like follow-up questions which we can take offline. That's easy. But in general, I think like there's of course like some overhead for scheduling kernels, but probably the most critical thing is that of course I lose this shared memory like synchronization and data exchange,
Correct.
which is possible inside the fused.
You lose that,
kernels.
yeah. You lose the state of your data that executes in a current asset, yeah.
Yeah, but as soon as I basically have in HBM memory, basically the synchronization or the like communication between different stages, then it's like, yeah, it's if there's like, all the kernels are already scheduled, basically not my CPU is blocking anything, then it can be also like pretty fast, right? So it's
you can do it at the L2. You do not have to go to HBM, so it's going to be faster for sure. So right, so you actually have that, but you trade certain resources. So when you launch too much work, you actually are trading certain resources in your hardware queue still, right? So you do have certain overhead that comes in. Your launch overhead for a new warp that get executed, because it's going to consume some resources to check whether I have a work to do or not work to do. That is still a check that I have to do, right? So that work is going to get bombarded. So there are trade-offs. These are all different trade-offs that you come into. And trust me, the Izzat is a great person to speak about this. He has talked about how to do this persistent kernel launches and execution in compiler level, and how to do aggregation of different work from different warps and different work streams together to manage a large persistent launch of the work, and then schedule it correctly, co-locate it correctly, maximize your L2 for the throughput and whatnot, just with the compiler optimizations. And I think we should ask this question to him.
All right, folks, I apologize. I think we might need to do like a time check because we have 3 minutes left. Kapil, like, thank you so much for this. Like, I really enjoyed the talk, and I really enjoyed like how you walked us through sort of like real world models and optimizing them. I think this was very, very helpful. I think it did showcase like some serious gaps we have in like teaching torch compile. So I'll take that feedback very seriously and, you know, figure out like who to bring in or teach the stuff myself.